Hi, this is Dr. Bricker here with a review for Exam 2. So Exam 2 will be Wednesday, and it covers these chapters 5, 9, 10, and back to 6. So applications of Newton's laws, momentum, energy, and circular motion. How would I study for this test? Well, I would definitely go over the practice exam, go back over the homeworks that we've covered concerning these chapters, read back through the chapters, at least if you don't have time to read the whole chapters, read the summaries at the end of the chapters. There are 14 questions on the actual test, just like the practice test. Same format as the first exam, multiple choice, but you have to show your work, and you'll see that you know that you get partial credit for that. Okay, let's take a look at the actual exam. One difference between the practice exam and the actual exam is you'll have more room in between the problems, so they won't be so crunched together like the practice exam. So you'll have more space. Let's see the first one though. A bead is moving with the speed of 20 meters per second at position A, so 20 meters per second here. And the track is shown in the picture. This track is friction-free. Okay, great. No appreciable air resistance. What is the speed at position C? So we want to know the speed here at C. Well, one thing we know, the total energy at A is equal to the total energy at C. And the total energy at A is made up of kinetic, because it's moving, and also gravitational potential. The total energy at C is the same thing. It's made up of kinetic and gravitational potential. Now there's less gravitational potential here because we're not as high, so there must be more kinetic, and that's how it should work out. So let's put the details into play here. Okay, so again we have gravitational potential energy at A plus kinetic energy at A. It's going to be equal to the gravitational potential energy at C plus the kinetic energy at C. Now the gravitational potential energy at A, let's call this YA, the height at A, and this one over here could be the height at C. We'll have mgYA plus 1/2 mvA squared, putting in the details of what the kinetic energy is. This will give us mgyb plus, C rather, plus 1/2 mvc squared. Okay, so mgYA plus 1/2 mvA squared is equal to mgyc, that's the gravitational potential energy at C, plus 1/2 mvc squared. Then the masses actually all cancel out because there's a mass in every term. And then the only thing that you don't know is the velocity at C. So you have to do some algebra. You know, G is 9.8, that sort of thing. And I'll just put dot, 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 do some algebra. You can get the velocity at C. Okay, so you'll definitely see something like this. This is a conservation of energy problem. Okay, number 2, block of mass 5.6 kilograms. That's the little m here, 5.6. Moves on a frictionless surface with initial velocity of 6.5. So little m moving at 6.5. To the right, collides with block big M, which is at rest, as shown. After the collision, the 5.6 kilogram block recoils to the left. Okay, so this one goes to the left. If the blocks are in contact for 0.2 seconds, what is the magnitude of the average force on the 5.6 kilogram block while the two blocks are in contact? Okay, let's take a look at this. Okay, so little m is 5.6. Initially it's moving at 6.5 to the right, then it recoils to the left. So I've got to put the minus sign there because it's going back the other direction. And then we have this other mass that's at rest. So big M, we don't know how much big M is, and it's initially at rest. We know that the collision takes 0.2 seconds. Okay, whenever you see a collision problem, we have the impulse relationship. F delta t gives you the change in momentum. This would be the final momentum minus the initial momentum. So mv final minus mv initial. And again, this is called impulse. I didn't put the vector sign above these, but just remember that you have to look at the x direction separately from the y direction. Luckily for this collision, it only happens in the x direction. Okay, so let's just focus in on little m here. So little m has a change in momentum. It's going one way, now it's going back the other way. We could figure out the change in momentum. We know the amount of time it takes for the collision. We could figure out the average force. So this is just for this one. So F delta T mv final minus mv initial. So the average force then would be mv final minus mv initial over the amount of time. Okay, so this answer will actually come out to be negative, and we're just looking at, we just want the magnitude of the average force. So this is the force on little m from big M. It's the same value for the force on big M from little m. Okay, so this is one sort of problem to look at. It's a collision problem. Another one would be, first of all, this is how we've solved this problem. That's all you need to do to get the answer for this problem. But what if we wanted to figure out how fast this mass was moving after the collision? So this final speed, how much is this final speed? Just say that we know what this is, so the mass is actually given. So this is a perfectly good problem, but let's take it a step farther. So same thing here, little m moving this way, this way. Assume that we know the value of big M, and if it's initially at rest, what's the final speed after the collision? Then we could take a look at this. Initial momentum of the system is equal to the final momentum of the system. So we would have little m v1 initial plus big M v, whoops, this is supposed to be little m initial. Same thing here, this is big M initial. Let me start over. Little m velocity of little m initial plus big M velocity of big M initial. That's the momentum of the system before. Little m velocity little m final, that's the speed after the collision, plus big M velocity big M final. And actually this term is 0 because it's at rest initially. So this is before the collision, what's going on. This is after the collision. And then you could actually figure out the speed of big M after the collision. I'll just put dot, dot, dot. Well, let me just write it down. Just finishing this step of algebra here. Minus mv little m final divided by the total mass. Okay. So again, we solved the problem that was asked, but just be aware of this collision type problem as well. Okay, let's look at the next problem. Okay, so number 3, pulling out of a dive, a pilot of an airplane guides his plane into a vertical circle, okay, with a radius of 600 meters, so something like this, and we'll draw it out. At the bottom of the dive, the speed is 150 meters per second. What is the apparent weight of the 70 kilogram pilot at this point? So when you're reading this for the first time, you have to ask yourself, what type of problem is this? And it's a circular motion problem. So all the circular motion information that we have on our formula sheets should go into this. So let's take a look at it. Okay, so here's the free body diagram at this location. And notice I'm drawing the normal force bigger than the weight. There has to, or bigger than the weight, yes. There has to be a net force towards the center, so the normal force has to be bigger than mg. So the radius that we're going through is 600 meters. Here's the speed, here's the mass. And they're saying, what is the apparent weight? In other words, how much is the normal force? So we know the net force is ma. It's a special kind of a now, towards the center. mv squared over r. And then it's up to us to fill in what goes in this box here. And I'm going to put normal force minus mg. That'll give us a net amount towards the center. And then a little bit of algebra from this point, mv squared over r plus mg will give you the normal force. And then we have everything to solve it here. Now it's just plugging in the numbers. Mass, speed, here's the radius, mg. So we did several problems in homework 7 dealing with this idea. Take a look back at one that looks just like this. If you're going through a dip in the road, so here's a car going through a dip in the road, it would be the exact same problem. So you'll definitely have a circular motion problem. Remember, you're always looking for the force towards the center. Okay, next we have number 4. 1,000 kilogram car experiences a force of 9,500 newtons, so mass, force, while slowing down from 30 to 15.9 meters per second. Okay, so mass, force, velocity. How far does it travel? So what's the value of the distance? So when you see these things given, mass, force, velocity, and we're asked for the distance, I think the work energy theorem right away. Now you could figure out the acceleration because you know the net force and the mass. You could figure out the acceleration, and then knowing the initial speed and the final speed, you could use kinematics to actually solve this. But we could use the work energy theorem. Let's do it that way. Okay, again, here's what I know. The work energy theorem is this. The net work, FD cosine theta, it's the change in kinetic energy. And this will be 1/2 mv final squared minus 1/2 mv initial squared. Now I know the net force. I'm trying to figure out D. The net force is lined up with the way that I'm going, so you know theta is 0 here. The force is this direction. The displacement is this direction. The angle between F and D is 0. So they're lined up with each other. So let me pick out this part. FD cosine of 0, which is 1. This would be 1/2 mv final squared minus 1/2 mv initial squared. And then I could solve for D. 1/2 mv final squared minus 1/2 mv initial squared divided by the net force. So definitely look for one like this on the actual test, the work energy problem. And just a clue again is if you know, actually, you know the net force here too. So if you know the net force, the mass, velocity, distance, any 3 out of those 4, you could solve the problem. This was 9,500 newtons. Okay, excellent. If you did do it the other way where you got the acceleration, then you use kinematics, that would be fine as well. 5th one, we've got 3 objects moving along a straight line as shown. Okay, good. Taking the positive direction to be to the right, what's the total momentum? So we've got to add these things up. So for the first one, remember what momentum is, first of all, mass times velocity. This would be 8 times 5, right, mass times velocity. This would be 40 kilogram meters per second, and it's positive because it's towards the right. And then the next one here, 4 meters per second, but that's to the left, times 15, so minus 60 kilogram meters per second. And then finally we've got this one, 3 kilograms times 2 meters per second, so plus 6 kilogram meters per second. So when you add those all up, you get minus 14. So there'll be a problem. This isn't a super difficult problem, but it is if you don't know that to the right is positive, to the left is negative. So you'll have a similar one to this on the actual test. Okay, so as shown in the figure, we've got a 4 kilogram mass moving at 5 meters per second, horizontal frictionless surface towards an ideal spring that's attached to the wall. After the block collides with the spring is compressed by 0.68 meters. What is the speed of the block when the spring is compressed by only half the maximum distance? Okay, so let's sketch this out. And it says here the actual exam will have multiple choice answers. So the practice test I didn't have a chance to make some answers, so the actual test will have that. All right, let's do this problem. Okay, so first let me say that this problem is probably just a little bit too involved to put on the actual test, but what I probably would have put on the actual test is something like, you know, what is the spring constant? We'll completely do the problem, but again, it's maybe just one step too much. But that's okay. If you can do this one, you can definitely do the one on the test. So we've got this mass moving with some initial speed. It hits a spring and compresses the spring. So basically what we're doing is taking kinetic energy here and turning it into spring potential energy. So let's first of all figure out the spring constant. So this kinetic energy is being utilized. It's being turned into spring potential energy. We had a homework question just like this, by the way. So we've got 1/2 mv initial squared. That's the initial energy of the system. It's all kinetic. And then it becomes spring potential energy, 1/2 kx squared. And I call it delta x here. It's the same thing, delta x squared. Okay, so we could figure out the spring constant. The 1/2s cancel out. So we have mv initial squared divided by delta x squared. That will give us the spring constant. So when you put the numbers in, we have everything here, you get something like 216 or so. And this would be newtons per meter. Whoops. You get 216 newtons per meter. Okay, so that's the spring constant, and again, that's probably about the level of the problem I would put on the test, taking kinetic energy, turning it into to spring potential energy. I'm not saying the tests ask you to figure out K, but you know, either mv, K, or delta x. Now for this particular problem, now that we have the spring constant, we can go back to the actual situation that they're talking about. What is the speed when the block is compressed by 0.34 meters? Okay, so in that problem, we have an initial amount of kinetic energy. That's before the collision. Afterwards, it's still moving because it's only compressed half as much. So we've got the final kinetic energy plus some different amount of spring potential energy. I'll just call it spring potential energy prime or something. So we would have 1/2 mv initial squared. That's the initial energy of the system. Then we'd have 1/2 mv final squared. That's what we're trying to figure out here, the speed after the spring is compressed by half as much. And then the spring part of it would be 1/2 k, same k because it's the same spring, and now it's compressed by a different amount, so I call it x prime. So the x prime, it says it's compressed by half as much, so 0.34 meters. Good, and then you have everything to solve this. The 1/2s go away, and we're trying to figure out what's the speed when it's compressed. In other words, how much is v final? Again, so we know the mass, the initial speed, we still know the mass, we're trying to figure out the final speed, and k we found from the first part, x prime, they tell us it's half as much. So you have everything, do some algebra, figure out this final speed. Okay, so that's how you solve the actual problem, but again, you know, look at something more like this. Okay, excellent. Next one here, which has the larger kinetic energy, a 50 kilogram object moving at 40 or a 1,000 kilogram object moving at 20. So it says kinetic energy, not momentum, kinetic energy. So something smaller moving faster, something larger moving slower. Well, you have to actually figure it out. Use this 1/2 mv squared. Do that for each of them. Do that for this one, do it for this mass, and figure out, and then just see which one has the larger amount. So even though they have maybe the same momentum, they don't have the same amount of kinetic energy. It's kind of a weird concept to think about. So actually do this for each of them. Do it for the 500 kilogram mass, do it for the 1,000 kilogram mass, and see which one's going faster. Or, it's not faster, which one has the bigger kinetic energy, rather. Number 8, the coefficient of static and kinetic friction between a 3 kilogram box and a horizontal desktop are 0.4. Okay, so that's for static, 0.3 for kinetic. What is the force of friction when a 15 Newton horizontal push is applied to the box? Okay, so this is going back to chapter 5. Let's take a look at this. Okay, so the coefficient of static friction, coefficient of kinetic friction, and they're actually given 0.4 and 0.3. Okay, we know the mass. That's also given here, 3 kilograms. And we're applying a force, some outside force of 15 newtons. And we want to see how much friction is. Let's draw the picture for this one. So normal force, mg, we're applying 15 newtons here. How much is friction? So with this sort of problem, we have to figure out which regime are we in. Are we talking about static friction or kinetic friction? So for static friction, it's less than or equal to the normal force times mu sub s. The maximum amount is when it's actually equal to the normal force times mu sub s. So with this kind of problem, we have to figure out how much is the maximum static friction, and then see if our applied force is larger than static friction's maximum. So let's do that. So the maximum amount would be the normal times mu sub s, which is mg times mu sub s. Okay, the mass is given 3 kilograms, 9.8 meters per second squared, and then times mu sub s, which is 0.4. So when you put all these together, you get 11.76. So our applied force here has exceeded the maximum amount of static friction. So that tells us we're in the kinetic friction regime. So kinetic friction, normal force times mu sub k. In the picture, mg times mu sub k. Put all those values in for mg and mu sub k, you get 8.8 newtons. Okay, so that's solving this problem. We've exceeded static friction because 15 is bigger than 11.76. So that tells us we're in this kinetic friction area. Okay, so that solves this problem. What if the applied force was only, say, 6 newtons? So let's do a completely different problem. Same thing, but now instead of 15, this is 6. So if I apply 6 newtons here, that's less than the maximum amount of static friction. So static friction would only be 6. It's only as large as it needs to be. If I apply 8 newtons here, static friction is 8 newtons. 10 here, static friction is 10. If I apply 11, static friction is 11, all the way up until I exceed 11.76, and then it becomes kinetic friction. Okay, so there's definitely one of these on the test. Make sure that you first of all figure out static friction, compare it to the applied force, and see which regime you're in. Okay, number 9, a push of magnitude P here acts on a box of weight W. Okay, so that's the M times G. The push is directed at an angle below the horizontal, as the picture shows, and the box remains at rest. Okay, the box rests on a horizontal surface that has some friction, and we want to know something about the normal force. Okay, so free body diagram. This would be P. This is theta. Well, there's got to be friction back this way if it's not moving, and then we must have a normal force here. So definitely a free body diagram helps in this case. This part over here would be P sine theta. This part of P over here would be P cosine theta. Right, so again, if this is theta, the opposite side, let me just draw it over here. Sine of theta would be the opposite side. I guess I could call this like Py if I want to. Would be Py over the hypotenuse. So then P sine theta is Py. That's how I knew to get this. And you could do the same thing over here. The cosine theta, and let me call this one Px, is the adjacent side, which would be Px over P, and then P cosine theta is Px. If you're having trouble seeing how I got P sine theta, P cosine theta, it's this little argument over here. Okay, and then to solve this actual problem, how big is the normal force? Well, the normal force has to be equal to P sine theta. Whoops, and I forgot the weight. Let me add the weight in here. So the normal force is up. It's got to be equal to whatever is down. So we've got normal force up equal to the weight, which is down, plus P sine theta. Okay, so that solves the vertical direction here. Whatever's up is equal to whatever force is down. You also know that the frictional force, which I have drawn to the right, has to be equal to P cosine theta to the left. So you'll see a similar problem on here. Just be aware, we saw the vertical direction. Be also aware of the horizontal direction. Okay, number 10. we have a 0.14 kilogram baseball, so mass 0.14 kilogram, thrown with an initial speed of 27.1 meters per second. It's struck by a bat with an average force of 5,000 newtons. It results in a velocity of 37 meters per second in the opposite direction. Okay, so opposite direction means I've got to put the minus sign in here. How long were the bat and ball in contact? So what's the time here? So look what we have. Mass, velocity, force, and time. Again, think of the impulse relationship. So F delta T, change in momentum, mv final minus mv initial. Okay, so one thing that I also know is if we're moving to the right, this force has to be the opposite direction too. Let's set this up and it'll appear to you, I think, why that should also be negative just from the way it's set up here. So the amount of time that we have, that's what we're looking for, comparing this and this. The amount of time would be mv final minus mv initial divided by the force. So when you put the numbers in, this will be m, v final is negative, minus m, v initial. This time will come out negative unless you realize that this force really should be negative because it's in the opposite direction of the way the thing is moving. Okay, key thing is here though, if you're going to call this positive, this one's got to be negative. If you don't do that, you'll get the incorrect answer. Okay, so mass, velocity, force, time. Think of this impulse relationship. Excellent. Okay, so next we have a 1,000 kilogram whale swims horizontally to the right with a speed of 6 meters per second. It suddenly collides directly with a stationary seal. Oh, it's a collision problem. Okay, good. Seal of 200 grams. The seal grabs onto the whale and holds fast. What is the momentum of the two creatures just after the collision? And we can neglect any drag effects. Okay, so let's just call the whale mass 1, 1,000 kilograms, initially moving at 6 meters per second. Then we've got mass 2 over here, which is the seal, 200 grams, and it's initially at rest. Okay, and we want to know what is the momentum of the two creatures just after the collision. Okay, well, I know that the initial momentum is equal to the final momentum. So if I can figure out the initial momentum, it's going to be equal to the final momentum. So the initial momentum is just contained in the whale because the seal's not moving. I'll write it down, but it's equal to 0. Okay, plus mass 2, velocity 2 initial. And that's equal to the final momentum. Okay, good. And then again, this one's not moving. So we would have 1,000 kilograms times 6 meters per second. So if the initial momentum is 6,000, that's going to be the same thing as the final momentum. Okay, now if I wanted to take this problem a step farther, I could figure out the speed of the whale seal combination afterwards. I mean, this solves this problem. This would be equal to mass 1 plus mass 2 when they're combined, multiply it by their common final speed, and I can figure out how fast they're moving afterwards. So this would be, you know this side's just a number, 6,000, equal to mass 1 plus mass 2 times their combined speed. And then you can figure out their combined speed. So take a look at that problem too. I mean, this is a perfectly good one, but how would you figure out their final speed? Well, I've done it for you here. I just want to do one more step, so let me take this down here. This would be 6,000 kilogram meters per second divided by the total mass, which is 1,000 plus 200, right? 1,000 plus 200 divided by 1,200. And then you can get their speed that way. Looks like to be about 5, right? So that makes sense too. If the whale was swimming at 6, grabs a hold of the seal, Now the mass is greater, so the speed's going to go down. All right, good. Let's look at the next one. Swimmers at a water park have a choice of 2 frictionless water slides. So this one goes straight down. This is more of a curved path. Although both slides drop from the same height, as it says here, this one's straight down, this one's curved. How does the speed of swimmer 1 compare to the speed of swimmer 2 at the bottom? Well, it turns out that they're going to be the same. In each case, we're taking gravitational potential energy and turning it into kinetic energy. So they each have the same mgh. So therefore, they're going to have the same speed at the bottom. And the m's cancel out. So 2gh, the square root of that is equal to v. Right? Multiply both sides by 2, take the square root. So then you could say same h means same v. Okay, lots of ways of explaining it. I mean, I did it numerically here, some numbers, and then I drew a conclusion from that. You could just kind of, if you wanted to, say this in words. You don't have to have the exact same way I've done it here, just as long as you explain it. Okay. Let's see, number 13. When an object moves in uniform circular motion, so first of all, what is that? It just means constant speed. The direction of the acceleration is, well, we already know, I've said it a lot, towards the center. So the acceleration is always directed towards the center. Here's the magnitude of it. Let's see these answers. Depends on the speed. Well, it doesn't depend on the speed. It's always going to be towards the center. Is directed towards the center. So it's not away from the center. In the same direction as the velocity. That's definitely not true. In the opposite direction of the velocity. No, for circular motion, it's towards the center. This would probably say explain. I mean, I guess I would say v is constant. We have an acceleration because the direction is changing. Okay, so acceleration because direction is changing. And it's directed towards the center. Directed towards center. That would be fine. A similar question is, what's the magnitude of the acceleration? And just because the speed is constant doesn't mean that there's no acceleration. It's because the direction is changing we have an acceleration. Okay, and finally the last one. 3 boxes are being pulled along frictionless floor, constant pull P, okay, here. The boxes are connected by very light horizontal strings, and this is T1 and this is T2. Which of the following statements about the tension is correct? And it says there could be more than one correct choice. But on the actual test, there will just be one of these, A through E will be correct. All right, well, let me take a look at the free body diagram for the first one here, this 10 Newton force. So I've got P, T1. I'm just looking at the horizontal part of the free body diagram. So it's a frictionless surface. That means that this thing's going to be accelerating. So if I just look at the free body diagram for the 10 Newton mass here, P has to be bigger than T1 for this thing to be accelerating. Now if I look at the free body diagram for this one, I would have T1 and T2. So this is for this free body diagram here is for this one. This horizontal part of the free body diagram is for that one. So I know that T1 has to be bigger than T2 for this 20 Newton mass to be accelerating that way. Let's go through these choices and see if I could weed some of them out. So T2 is equal to P. Well, that's definitely not true. I mean, P's got to be bigger than T1, and I know T1 has to be bigger than T2. So P bigger than T1, that's bigger than T2, just from these horizontal free body diagrams. So it can't be this one. T2 is bigger than T1, so that cannot be true either. I mean, you see, looking at this free body diagram for this one, this force has to be bigger than that one for it to be accelerating. T1 plus T2 is equal to P, so let's come back to that one. T1 equal to P, well, that's not true. We saw it from this. T1 bigger than T2. Okay, so that does work out. So it's a little trickier to show that this one's not true, but let's give it a try. So let me look at this mass now. And I could say that the net force on this mass, really the mass would be 100 newtons, that's the weight, divided by g. So that's the mass of this one, times the acceleration would be equal to T2. This is using Newton's second law. Net force is ma times T2. That's for the 100 Newton weight. Then let me go to this one over here. So the net force on this one would be the mass. So 10 newtons divided by 9.8. Doing the Newton's second law for this mass times A would be equal to P minus T1. And then it follows from this, doing a little bit of algebra, T1, moving this to the left-hand side, this would be P, so moving this to the left-hand side, moving this thing to the right-hand side, 10 newtons divided by 9.8 meters per second squared. So again, this is Newton's second law for the 10 Newton weight. So ma, P minus T1, do a little bit of algebra, so T1 to the left side, 10 newtons divided by 9.8 to the right-hand side, and I get this. So here's T1, here's T2, and then I can just add them together and see what I get. So T1 plus T2, just literally adding these things together, this would be equal to 100 newtons over 9.8 times A. That's what T2 is. I wrote T1 plus T2, but I'm starting with T2. 100 newtons divided by 9.8 times A. That's the T2 part. And then T1 would be P minus 10 newtons over 9.8 meters per second squared. And then you see T1 plus T2 is not just equal to P, it's equal to something else. Whoops, I'm sorry, let me regroup on that one. So T1 plus T2, this is the T2 part here, plug that in. Here's the T1 part, P minus 10 newtons over 9.8. And then you see that T1 plus T2 is definitely not equal to just P. There's some other value involved here. That's really a rigorous mathematical way of saying it. You could say, when you're looking at the system, P has to be bigger than any of the internal forces for us actually to have an acceleration to the right. That would be the simpler way of doing it. Okay, great. Any questions, email me. Again, the actual test is 14 questions, hopefully very similar to the practice test. And just like before, make your own formula sheet, both sides, handwritten, put whatever you want on there. Okay, talk to you soon.